All right, for 15.6, which is all about surface integrals, I want to start by taking a step back, relating this to stuff that we've already done, and then comparing it to what we're doing in this section. Okay. So we've done line integrals. We've done simple line integrals, and then we did line integrals of a vector field. Okay, so a simple line integral is something like you have a single integral of some function, f of, let's say, x, y, z, times a tiny ds. Okay, so you've got some particle traveling through space, or you've got some curve. You say line integral, but it's really more of a curve integral. Let's say you want to travel from point A to point B. A simple line integral in context is usually, your function is usually something like a density function, rho of x, y, z, times your tiny ds. So this rho, since it's a linear density, is something like maybe grams per centimeter. And then this thing is a tiny little length of your curve. So that's going to be times a centimeter. So when we multiply grams per centimeter times a centimeter, we should get something where the units are in total centimeters. Or total, sorry, the centimeters cancel, we get total grams. Okay, so that's why we would use a line integral if our function is something like a linear density or charge density to find a total mass or a total charge if this were a charge density as for some kind of curve traveling through space. Now a line integral of a vector field is a little bit more complicated. Okay, so for a line integral of a vector field, we might have that same path in the xyz plane. Okay, say we want to go from point A to point B, and we've got some kind of a vector field. Who knows what this vector field is doing? But we've got these vectors in our vector field that are going in. Some are big, maybe some are small. Okay, but we want to know from point A to point B. The line integral of a vector field is defined as f dotted with t over your tiny ds. Okay, over your curve, so times your tiny ds. So at any point here, we want to know for one of these vectors, as you travel in this direction from here to here, you want to know how much of this vector field at any given point, so let's say there's a curve from your vector field that looks like that. Then you look at your tangent vector, r prime of t, and you want to know what component of this vector field is in the direction of your tangent. So if we think of this as a velocity vector field, there's a component of your vector field that's actually helping your particle move in the direction that you want to go. It's not necessarily going exactly in the same direction. But the line integral of a vector field is defined as the amount of work done by the vector field in moving your particle along your curve. Okay, so it's the amount of work done by your vector field. How much work is this vector field doing to help you move from point A to point B along this curve, traveling through this vector field? Okay, and the way we calculate that is you've got your vector field dotted with t. Now that's a unit tangent vector. It's in the direction of r prime of t, the derivative of your position, divided by the magnitude of r prime of t, times your ds. Well, the ds, if you can remember what that is, that's the magnitude of r prime of t dt. So these cancel, and the way you calculate that is f dotted with r prime of t dt. Okay? So there's your line integral of the vector field. Here's your line integral. Okay? Now, let's talk about a surface integral and then a surface integral of a vector field. So a surface integral of a vector field is better known. We usually don't call it that. It's called flux. Okay? So that's, a lot of times we think of that in context. It's like the amount of flow that travels through a surface. Okay? So a simple integral is like a simple surface integral is like a simple line integral. It's a double integral of your scalar function, f of x, y, z, over a ds. Now this ds, that's a capital DS, that represents not just a tiny length of the curve, but a tiny area of your surface. So if we go back to this picture from the previous section, if you wanted to find this, we're finding the area of this surface, we look at something like this here, one of these tiny little parallelograms, and that would be your tiny little ds. Okay, that's the area of one tiny little parallelogram. Okay, so the way we calculate that double integral of your f of x, y, z times, well, that thing is going to be the magnitude of our u cross our v times du dv. Okay, so technically we already did a surface integral when we find the area of a surface. If your f of x, y, z is just 1, then you'd have a double integral of 1 ds, and that is just your area of a surface. Remember, the area of a surface was just double integral of the magnitude of our u cross our v du dv. Or we also said if your parameters, instead of being u and v, were x and y. Okay, let's say we had x, y, z, were x and y, and your z was a function of x, y, so let's call it g of x, y. Okay, and you did your cross product, rx crossed with ry. You ended up getting something that looked like opposite of dg dx, opposite of dg dy, and 1. So the magnitude of rx cross ry was equal to the square root of 1 plus dg dx plus dg dy. Sorry, that's squared. Okay, so your area of a surface could also be written as square root of 1 plus dg dx squared plus dg dy squared dx dy. Okay, so that's area of your surface, just to recap that. So this, you can do the same thing up here. You can also find a surface integral. Even if you have a function, this thing would be your f of x comma y comma z of xy, so g of xy, if z is a function of xy, y. And then you have the square root of 1 plus dg dx squared plus dg dy squared dx dy. So a surface integral is calculated in one of these two ways. Okay. This way, if you parameterize your surface in terms of u and v. This way, if you parameterize your surface in terms of x and y. I mean, you can always use this. But this is a little bit simpler. It's what it turns out to be when z is a function of x and y. Now let's talk about flux, a line integral of a vector field. Talk about what that means. Okay, so now I'm going to look at this picture over here. Let's say we've got this surface and we've got these vectors represent the vector field. We want to know how much of this flow is passing through this surface. Okay, so how much of the flow is passing through this surface? Well, we're not going to take a dot product of the vector field with a tangent to this surface. That wouldn't make sense. We want to know, so we're going to take a tiny little ds. Okay, and then we want to know how much of this is in the direction of the normal to the surface. So let's say our normal to the surface goes this way. And I'm going to make it a unit normal. And let's say our flow of the vector field is going in this direction. So that's your F. You want to know what component of this is going to pass through the surface. Now you might be wondering, well, why do we want to do that? Well, think about a picture like this. If our surface looked like this, think of this as fluid flow. Let's say this is a fishing net underwater. You want to know how much of this water is passing through the surface. Well, if it's passing right above or right below, not as much as passing through the surface. But if your water is flowing this way, well, there's a lot of water passing through this surface. Okay? In order to find how much is passing through the surface, you're going to take that vector field and you're going to dot it with the normal. That's going to give you the component of the vector field that is traveling in the direction of your normal. Okay? So if you take the component of this vector, remember this vector has a magnitude and a direction. You would project it onto the normal, so it would look something like this. That's how much of this vector field is passing through the surface. Okay, so The way we calculate this is we're going to take flux is equal to the double integral of f dotted with your normal times your big ds. Okay. Now, in a context of fluid flow, your f is really like a density times a velocity. Well, your density is something like, I don't know, grams per centimeter cubed, because it's a cubic density. And your velocity is something like centimeters per second. Okay, so then one of the centimeters cancels, and this comes out to be grams per centimeter squared per second, which makes sense. How much of this fluid, grams per centimeter squared, or you could think of grams per second per centimeter squared. So how many grams per second are passing through the surface per centimeter square of the surface? Okay. So the way that we calculate that, that's going to look like this. This F in that context would be like a rho times a V. Either way, that's your vector field. Your normal, remember how to find a normal to a surface if we go back to this picture. Your normal to the surface is in the direction of the cross product of your two partial derivatives. The RU is tangent to your surface, the RV is tangent to your surface, so the plane formed by those two is going to be tangent to your surface. Their cross product is perpendicular, which will represent a normal to the surface. So that's going to be RU crossed with RV. To make a unit normal, it's going to be the magnitude of RU crossed with RV. And then remember what the ds is. That's a magnitude of RU crossed with RV, du dv. Okay, these cancel in the simplified version of flux. It's double integral of this thing. I'm going to go back to calling it F because that's more general than one specific scenario. You're going to take your F and you're going to dot it with the RU cross RV, du dv. Okay, that's how you calculate flux. Now, there is a simplified version of flux if, again, z is a function of x and y. So let's say you have r of x, y, z. Z is a function of x and y. Okay, so if you have r defined as a function of this, so you'd have x, comma, y, comma, g of x, y. Now your vector, your cross product rx crossed with ry would be opposite of dg dx, opposite of dg dy, 1. So this thing becomes double integral of f dotted with opposite of dg dx, opposite dg dy, comma 1, dx dy. Okay, and a lot of times if f is in the form of m, n, p, you're dotting that with opposite dg dx, opposite dg dy, 1. Sorry, can you see that? So I just replaced the f with m, n, p and brought this down, dx dy. So that becomes a double integral of, we multiply these together, opposite of m, dg dx, minus n times dg dy, plus p, dx dy. Okay, so that's how you're going to calculate flux. This one up here we can also simplify if we replace the m with, actually that's not an easy word, that's the easiest way to write that one. Okay, so you're going to use this one or this one. Okay, this is the one you use, and you see this a lot in the book when z is defined as a function of x and y. In the next video in part 2, I'll do a couple examples.